So for standard form, it works well. For standard form, we have our answer of the model of this Sydney Harbour Bridge is minus 2 over 49 x squared plus 2. All right, so as I said, this first standard model in this case is probably the most complicated way of doing this out of all three. But as I said, I did it just because it was the first one there. Now that we've got the complicated bit out of the way, and that I've scared half of you already to get off to stop the video and move on to doing something else. Now what we can do is go on to the second one. So here we have vertex form. All right, so let's get a nice large eraser. Have you guys copied it down? Should I check your workbooks? Okay. So let's slowly, nicely get rid of all these so we have some space. Oh, you haven't copied? Why haven't you copied this one? Okay, I'll leave it for a second. All right. Okay, done. Can I take it off? Everybody, yes? Take off? No? Yes? Good. Okay, all right. Hey, come on, we always have to wait for you. All right, done? All right, good. All right, let's take it off. All right, taking it off. Let's go on. Oh, I cut out some of the equation as well. Oh no, I cut out too much. Let's just fix that up quickly. Freehand is not as good as ruler. All right, and here we also have this part connected. All right, good. Second form, the vertex form. All right, so the vertex form, it looks like this. Y is equal to a x minus h squared plus k. Okay, so from here, what we have is we have this point. So the reason it's called a vertex is because of the turning point. So here we have the h and the k being the coordinates for the turning point. So that's the h and the k. Where is the turning point with our equation here? With our function, I mean? Well, here on the graph we have, so it goes, we go up, 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 up. We slowly, the gradient starts decreasing until it gets to 0. When we start turning back downwards. Go back down. So therefore, turning point here is this point right here. So it's 0, 2. So therefore, h and k will be actually 0 and 2. So then what will that make our equation look like? So that will make our equation look like this. A x minus 0 squared plus 2. Which easier form is ax squared plus 2. All right, but again, we still don't know what is a. Well, how can we get a? Well, we can either use 7 or minus 7. Either one, because here we have a squared. This here is squared. Because we're going to square it, even if we use the negative 7, it's going to become 49. So we have y is equal to a, let's just say negative 7 squared plus 2, which is of course equal to a 7 squared plus 2, which is 49a plus 2. And the y, so when x is 7 or when x is minus 7, what is the y? So it's along the x-axis, therefore the y is 0. So here the y, so actually this is 0. Therefore we want to solve for a, so we go take 2 to the other side. We have minus 2 is equal to 49a, and therefore this sign means therefore a is equal to minus 2 over 49. All right, so we have found our a, and our h and k we knew. It was quite easy because we just directly substituted from the known turning point that we have identified from our graph. Okay, so therefore what we have is y is equal to, looking back at this form, a we know it's minus 2 over 49, 49 x minus 0 squared plus k, which is plus 2, which again can be rewritten as y is equal to minus 2 over 49, x minus 0 is just x squared plus 2, and surprise, surprise, does this look familiar? Well, if we write it down here, we write vertex form y is equal to, what do we have? It's right here, right? So we have minus 2 over 49 x squared plus 2, and again, surprise, surprise, they are equal. Either the standard form or the vertex form give the exact same equation as it should, otherwise we would perhaps have a different type of graph. Okay, so that is that for the second form. Now moving on to the third form.